Welcome to this video. In this video we'll be talking about the bisection method. So by the end of this video you will be able to use the bisection method to solve a nonlinear equation. So the bisection method is one of the bracketing methods, and it has a certain set of requirements for the method to work. First off, in a given interval from a to b, f of x has to be continuous, and somewhere there is a root, meaning somewhere in this interval from a to b, f of x is equal to 0. Now, generally speaking, there are two possible scenarios if there is just a single root in the interval. The first one is shown here on the left, so I have some function with an interval from a to b. And in this example here, at the left bound of the interval, f of a, if I plug in a into the function f of a is smaller than 0, and at the right bound, f of b is greater than 0. So we have these conditions, f of a smaller than 0 and f of b greater than 0. And the second possible scenario is the exact opposite, namely that on the interval from a to b, at the left bound of the interval, the function is greater than 0, and on the right side of the interval, f of b, the function is negative. So in this case, f of a is greater than 0 and f of b is smaller than 0. But in both cases, if you look at the product of f of a times f of b, you'll notice that because of the sign change in the interval, the product of f of a times f of b will be guaranteed to be smaller than 0. Provided, of course, that there is a root in this interval from a to b. So here's the procedure of the bisection method. The first step is to find this interval from a to b such that f of a times f of b is smaller than 0, meaning that there's guaranteed to be at least a single root in this interval. So let's assume here in this sketch that we have a function f of x that's shown here in gray that we're trying to find the root of, and we start out with an interval that we found where there is this guaranteed sign change. In this case here, f of a is smaller than 0 and f of b is greater than 0, so we have the guaranteed sign change. The second step is to calculate an initial estimate. How do we do it? Well, we calculate the initial estimate as the midpoint of the interval. So the formula is simple, simply a plus b, the left plus the right bound, divided by 2. That would be our initial estimate for the numerical solution of the root. The third step is to determine whether the true solution, meaning the root, is either in the left interval from a to the numerical solution, or in the right half interval from the numerical solution to the original right bound b. And then, depending on whether it's in the left or the right part, the true solution, we will update the interval. So in our example here, if we evaluate the function value at the numerical solution, which is the midpoint of the interval, in our example that would be a negative value. So here are the options, the three options that we have. If the product of f of a times the f at the numerical solution is greater than 0, then the true solution cannot be in this left subinterval. It has to be in the right subinterval, meaning from the numerical solution to the original right bound b. And in that case, then, we move the subinterval over and concentrate on the right portion of the original subinterval, meaning we move the left bound over to the numerical solution, which is the midpoint. The second option is that this product f of a times f of the numerical solution is negative, meaning there has to be a sign change in this left half of the original interval. In that case, we move the right bound over to the numerical solution, meaning the midpoint, such that we are now concentrating on the left half of the original subinterval. And then there's actually a third case, that the product of f of a times f of the numerical solution is equal to 0. Well, since f of a wasn't equal to 0, that would mean that the numerical solution is actually our true solution, because f of the numerical solution then would be equal to 0. With one little caveat, which we saw from module 1, we can have an underflow. So if f of a and f of b are so small that their product of these small numbers causes an underflow, that then would be set equal to 0, indicating that the numerical solution would be my true solution, but that is only accurate up to the finite precision arithmetics that we are using. So in our example here, we had the case that the product of f of a times f of the numerical solution is positive because both function values are negative, which means that we now set the left bound equal to the midpoint. We move the a point over to the numerical solution, and that now becomes our new subinterval that we're looking at. For this new interval, then, we update our numerical solution to be again the midpoint of this new subinterval. So the numerical solution would be a plus b over 2, would be right there in the middle. And then we would repeat steps 3 and 4 with this new numerical solution. We would decide whether the root would be in the left half of this new subinterval or in the right half of the new interval, and then accordingly adjust either the left bound A or the right bound B to zoom in onto our root. How long do we repeat these steps 3 and 4? Until the solution is good enough, as given by some error measures. So what could these error measures be? Well, for a bracketing method, we can calculate the tolerance in solution. So we could continue with steps 3 and 4 until the tolerance in solution, which is after n iterations, the right bound minus the left bound value, so b minus a divided by 2, is smaller or equal to some acceptable value, just here abbreviated as tolerance, okay. Or we could look at the tolerance in function, meaning that the absolute value of the numerical solution that we have after n iterations plugged into our function is smaller or equal to some okay threshold. Or we continue until the estimated relative error, meaning the nth iteration numerical solution minus the prior numerical solution divided by the nth iteration numerical solution, is smaller than some acceptable threshold value for the relative error. Okay, so let's do an example here, and we're going to try to find the root of the rather simple function x squared minus 1 equal to 0, and we're given here an initial interval from 0.4 to 1.4. That's where we're trying to find the root of this problem. So let's get going here. So we're given an interval. So we're given that a is equal to 0.4, and we're given that b is equal to 1.4. So therefore, the interval that we're looking at from a to b is the interval from 0.4 to 1.4. Now, it's a good idea to check whether there actually is guaranteed to be a root in this interval by finding out what is the function value of a and what's the function value of b, and see whether there is a sign change. So let's do this check here. I'm going to check whether there's a root in there. So I'm going to calculate f of a. So that would be f of 0.4, which if I plug this into the function here, this would be my f of x. That would be 0.4 squared minus 1. That's 0.16 minus 1. That is equal to 0.84. That's my f of a. And my f of b is equal to f of 1.4, which is equal to 1.4 squared minus 1. That's 1.96 minus 1 is equal to 0.96. So at this point, it would look like that there is no sign change, which is kind of surprising. And if I go back here, I notice that I made a mistake in here. So 0.16 minus 1 is, of course, a negative number. Okay, so now if I compare these here, their product is smaller than 0, meaning there is a root in this interval, as had to be expected. Okay, so this initial interval checks out. So I can then calculate my initial guess for this interval. So that's the numerical solution, and I'm going to write here as a superscript in round parentheses the index number, and I'm going to use the number 0 for the initial guess. So that's the midpoint of this interval. So a plus b divided by 2. That would be 0.4 plus 1.4 divided by 2. It's 1.8 divided by 2. That's equal to 0.9. So this 0.9 is my initial numerical solution guess. All right, so with this here, I could also calculate now the tolerance in solution, because I have an a and b. So that would be the absolute value of b minus a divided by 2, which is the absolute value of b was 1.4 minus 0.4 divided by 2. So the tolerance in solution is just 0.5 in this example. That's from the initial guess. So let's do the first iteration. So iteration number 1. And if we look at the algorithm up here, right, we've gone through these steps. We checked that the initial interval has a sign change. We calculated the initial guess and some error measure in order to check whether we might already be done. And then we're going to iterate on these steps 3 and 4, meaning we're going to update the interval either to the left half or the right half, depending on what the sign is of the product of f of a times f my numerical solution. So I know already what f of a is, right? That would be this value here. Let me just mark it. F of a, I calculated here, that's negative 0.84. That is my f of a. And now I need to calculate f of my numerical solution. But my numerical solution is the 0.9. So let's calculate f of the numerical solution of my initial guess. That's f of 0.9. So that's equal to 0.9 squared minus 1, which is equal to 0.81 minus 1, which is equal to negative 0.19. Okay, so here is the initial guess numerical solution that I used to calculate the function value at that point. Okay, so now I have to check what the sign is. So what is f of a times f of my numerical solution that I currently have? So that would be negative 0.84 times negative 0.19. And I don't really care about what that value is. All I care about is what the sign of this is. So that is greater than 0, right? I multiply two negative numbers, gives me a positive number. Which means now, because this is positive, I am going to set my left bound, because there is no root guaranteed to be in the interval from a to the midpoint. Therefore, the root has to be from the midpoint to the right, to the b value, and therefore my new left bound of the interval has to be equal to my midpoint, which is my numerical solution. So I'm going to set a equal to my numerical solution that I currently have, which now means that the interval that I'm looking at, ab, is equal to a was 0. The numerical solution, so 0.9, and my right bound is still 1.4. Okay, now with this new interval, I can calculate a new numerical solution. Right, that is now here at step number 4, update the solution to the midpoint and calculate the new error measure. So my numerical solution, iteration 1, is equal to the midpoint of this new interval, and the new interval is right over here. Right, so I have 0.9 plus 1.4 divided by 2. That is 2.3 divided by 2. It's 1.15. That is my new numerical solution estimate. And for this I can calculate, again, the tolerance in solution. In case that I'm done, right, this is accurate enough, tolerance in solution is still b minus a over 2, which is 1.4 minus 0.9 divided by 2. Absolute value, that is 0.25. That is my tolerance in solution for the numerical solution of 1.15. Okay, let's do one more iteration. Iteration number 2. So the process is now again check whether there is a sign change from f of a to f of my numerical solution. So I have to calculate what is the function value at my current numerical solution. So f of x and s1. That's f of 1.15. Let me mark this, see where that comes from, right? That's my numerical solution. Just going to plug this value into here. So that's equal to 1.15 squared minus 1. And that's equal to 1.3225 minus 1. That's equal to 0.3225. Okay, so now I have to check f of a times f of this numerical solution. So f of a, just got to check here, somewhere up here. So f of a, my a is 0.9. And I calculated somewhere f of 0.9, that's negative 0.19. So negative 0.19 times my f of the numerical solution, that's 0.3225. And the result of that is smaller than 0. So therefore, I have to set the right value, set b equal to my numerical solution. And therefore, my new interval from a to b is equal to, the left bound remains unchanged, 0.9, and the right bound updates to the numerical solution, 1.15. That's my new interval. And now for this new interval, I can now calculate what is my numerical solution. So x numerical solution 2 is equal to the midpoint. So a plus b over 2, that's equal to, well, we got 0.9 plus 1.15 divided by 2. That is 2.05 divided by 2, that is equal to 1.025. And now my tolerance in solution for this is b minus a over 2. That's equal to 1.15 minus 0.9 over 2. It's equal to 0.125. So we have a solution right now that says that after 2 iterations, my numerical solution for the root is 1.025 with a tolerance in solution of 0.125. Okay, and if of course looked at that equation x squared minus 1, the exact solution of that is plus 1 or minus 1. So we are trying to zoom into the plus 1 solution. And you see that this is a true statement, right? That the true solution is 1.025 plus or minus 0.125. Okay, that is the bisection method applied. Let's talk about some properties of the bisection method. If an odd number of roots exists in the interval, then this method will always converge. Why an odd number? Because that guarantees that there is a sign change between f of a and f of b. However, if there are multiple roots in the interval, then this method will find only a single root because it cannot detect an even number of roots. So we will only find always a single root only in the interval. So that means the initial interval should be chosen in such a way that ideally only one root lies in the interval. If there are multiple roots in the interval, the method will find one of these roots, but if I'm interested in the other roots, I have to come up with a new subinterval or a new starting interval that contains the other roots, an odd number of those. Now, how do I find this initial interval? So oftentimes that initial interval can be chosen based on some physical arguments that provide some rough estimate for the solution. After all, right, the nonlinear equation that we're trying to solve in engineering likely describes some physical process. So that will give us some hints of what the initial interval should be. Now the method will fail if f of x is tangent to the x-axis at the root point. Because as you can see here in the example, there is no sign change in the interval if the root is just tangent to the x-axis. Now, the method is guaranteed to find a solution, but the method actually converges relatively slowly compared to the other methods that we will talk about later on in the module. And you might have noticed in the example that the tolerance in solution is always decreasing by a factor of 2 each iteration. And that is kind of logical because we are always looking at a half of an interval to find our new subinterval. And that always divides the size of the interval by a factor of 2. Now, because we're checking for the sign of the product of two numbers, and these numbers, f of a and f of x numerical solution, are supposed to be small because at the true solution that value is 0, underflow can become a problem because we're doing the product of two small numbers. Now, one could theoretically avoid this by checking the sign of f of a and f of the numerical solution separately. But for engineering applications, that's typically not an issue if we're using double precision numbers, as is the default for MATLAB. All right, thank you for watching.